See how enzymes catalyze reactions in such a way that they enhance the rate of the reaction, we need to do a quick discussion of free energy. And this is actually important because we will be discussing free energy for most of the semester. Free energy expresses delta G, or Gibbs free energy. And delta G tells us how far a reaction is from equilibrium, because reactions are always trying to go to equilibrium. And we will discuss, I'll discuss on the next slide a little bit how that comes into play. But to start with, we need to know the difference between delta G and what we call delta G naught. So delta G naught is the free energy change for a system starting at the standard state. So that would be starting with everything at 1 molar, which generally we don't have inside a cell. We pretty much, the only thing that is present at a concentration that's anywhere close to 1 molar is water. Delta G, on the other hand, depends on delta G naught, as well as the concentration of reactants and products, which are not at standard state conditions. So delta G is kind of more along the lines of what's going on within a cell. If we consider a reaction where we've got A plus B going to C plus D, we can express delta G as delta G naught, so that's our standard state delta G, plus RT, where R is 8.314 joules per mole Kelvin. T is our temperature in Kelvin. Temperature usually is going to be 310 Kelvin, which is 37 degrees, which just happens to be body temperature for us. And that's all multiplied by the natural log of this right here is KEQ, which is the concentration of the products divided by the concentration of the reactants. Now, in terms of predicting spontaneity of a reaction, if delta G is positive, we have to put energy into the process to get it to go to equilibrium. So this is considered an endergonic reaction, and it is non-spontaneous. If, on the other hand, delta G is negative, energy will be released as the reaction goes to equilibrium. So this is considered an exergonic reaction, and it would be considered spontaneous reaction. Generally, we need to deal in spontaneous reactions because we need things to naturally occur. Sometimes we have to add a little bit of energy to make a reaction spontaneous, but ultimately we need our reactions to have negative delta Gs. We can also have a delta G of 0, which means that a reaction is at equilibrium. In this case, delta G of the products equals delta G of the reactants. And we might see, we don't see any change of concentrations. That doesn't mean that no reaction's taking place. If we have, A going back and forth to B at equilibrium, it means that for every molecule of A that goes over to B, a molecule of B has to go back to A. And that's basically what is going on at equilibrium. Now, delta G in biological systems is a little bit different than the standard state because most biological systems operate on a pH that's closer to neutral, pH around 7. So as a result, the biological standard state has to take into account that the concentration of hydrogen ions is about 1 times 10 to the negative 7th molar most of the time. For example, in our cells, it's a little bit different than that. It's actually pH 7.4. But we have to essentially take that into, we have to account for the pH of 7 versus standard state pH would say that H plus equals 1 molar. That's pH 0. There's not a whole lot of biochemistry that goes, or effective biochemistry that goes on at pH 0. So as a result, to take into account the fact that we have to run our reactions at pH 7, this gives rise to the delta G naught prime. So this is the free energy biochemical standard state. From this, we also get delta G prime, which indicates the delta G, non-standard conditions, but biochemical standard state, so pH of 7. And the importance of this cannot be overstated. We cannot use standard conditions because, once again, if we had 1 molar hydrogen ion concentration, our enzymes would basically be completely hydrolyzed to amino acids because the high hydrogen ion concentration would destroy the peptide bonds. In terms of how free energy and equilibrium are related, we saw earlier that delta G, and I'm going to rewrite this, delta G equals delta G naught plus RT ln KEQ. At equilibrium, delta G is 0. So what happens is we say 0 equals delta G naught plus RT ln KEQ. And if we want to isolate delta G, we got to subtract the RT ln KEQ. So we end up with delta G naught equals negative RT ln KEQ. And that's where this equation comes from, saying that our delta G at standard conditions, biochemical standard state, is negative RT ln KEQ. Now, if we want to calculate the delta G naught prime for ATP hydrolysis, we need to know the KEQ for this process. And we know that the KEQ has been measured at 2.23 times 10 to the fifth. That generally implies that a fairly large KEQ, large value, indicates that the reaction heavily favors the products. So if we plug all this in, our R value, 8.3014 joules per mole Kelvin, doing this at 25 degrees Celsius, and multiply that by our natural log of KEQ, we arrive at negative 30.5 kilojoules per mole. So that's the standard state delta G for ATP hydrolysis. Fairly exergonic reaction, fairly spontaneous, which is a good thing because ATP is what we use to derive a lot of energy.